Okay, this video is going to talk about the topics in Hartshorne's chapter 14. Specifically, we're going to look at Cartesian planes over any field. In this first video of section 14, we're specifically going to focus in on what's a field, so what you could expect to see when you see this thing called a field. Okay, so in terms of what we're going to be looking at, there's a bunch of things we'll see in section 14, but again, we're going to be focused on a field. So section 14 is the second section of chapter 3, and the idea behind chapter 3 is dealing with this notion of a Cartesian plane. Now you guys, if you're in this course, have all dealt with Cartesian planes before, and the most standard one is the real Cartesian plane, which we looked at in section 13. And remember, the real Cartesian plane was the same xy coordinate system, the x-axis, the y-axis, straight lines considered lines. We have circles, parallelness, perpendicular lines, ordered pairs for our points, all that fun stuff. This was the real Cartesian plane, was also, roughly speaking, the same thing as our standard model on R2. The only difference was once you have a Cartesian plane, you've got some extra things going on. Okay, so the difference between section 13 of the real Cartesian plane, where everything was based off of the standard model in R2, is now we're going to look at a Cartesian plane, but instead of being on R2, we're going to take out R2, or real numbers, and we're going to replace it with a set of numbers called a field. Okay, so that's the idea. Again, we are going to use these fields to build our different models of geometry, specifically chapter 13. Cartesian planes are the models of geometry. The interesting thing about building your geometry as a Cartesian plane is you start with a different set of numbers, you then build it the exact same way, and you end up with a different geometry. Okay? So, let's start off with a definition of a field. A field is simply a set. And remember, a set from, well, let's face it, we haven't talked about sets too much in this class, but I'm assuming you've seen the word set before, or at least you've definitely used them. A set is simply a collection of objects. Now, in our class, it's going to be a collection of numbers, but it could actually be any sort of object you want. Okay. Now, that set, we're going to call F because it's going to turn into a field. In math, people are lazy. But we're going to have two operations associated with this set. Now, how those operations are defined can get crazy fancy, but in our class, we're not going to do anything crazy or fancy. The operation tagged with the symbol that looks like a plus symbol is literally going to be normal addition, and the symbol that looks like a multiplication symbol here is going to be normal multiplication. Now, when I say normal multiplication, I do mean multiplication and also addition as is appropriate to your set of objects or your set of numbers. Okay. Now, here's the extra thing. Your set does need to be closed under addition and multiplication, and all that means is any sum that you grab. So pick any two elements in your set. When you add them together, it still has to be in that same set. And if you take any two elements in your set, when you multiply them together, they also still have to be in that same set. Okay. Now, that's just the basics. Here's the properties that turn you into a field instead of just a set with some operations attached. The first thing is that set F must be what's known as an abelian group with respect to addition. Now, I am not assuming in any way, shape, or form that you guys know what a group is or an abelian group. So everything under this, and I'm going to have 4 parts, subparts here, is really going to be the description of what it means to be an abelian group. Okay, so the first thing that you have to have in order to be an abelian group is you have to have what's known as the associative property. In other words, you add 3 items together, these 3 entities, A, B, and C, elements from your set F, which will eventually turn into a field. Take any 2, add them together, then add the third one, and it doesn't matter which 2 you originally started with. Now, interesting fact is both addition and multiplication are what are known as binary operations. That means they are only defined on 2 objects. So as soon as you're adding more than 2 objects together, this associative property actually comes into play. Now, have you done that have you added more than 3 objects or more than 2 objects together in the past? I'm sure you have. Maybe you thought in terms of parentheses, maybe you didn't. But technically speaking, if you have three objects you're adding together, there are invisible parentheses there, even if you didn't write them. Okay. Now, second thing you have is you have to be what's known as commutative with respect to addition. Commutative simply means it doesn't matter the order in which you add the two things together. And that has to work for any pair of elements you grab out of your set. Third thing is where you're dealing with something known as, and I'm going to give you both the layman's term as well as the technical term here. You have to have some element in your set F that'll act just like the 0. And that's saying acting just like the integer 0. What does the integer 0 have to do? You add 0 to any other number, and it's got to be that other number. Well, suppose your set isn't made up of integers. Suppose it's made up of other objects. In that case, one of the objects has to act just like the 0 would act. In other words, add it, however you've defined addition, to any other object, and you get that any other object. So what people will do when they're talking about fields is they'll often do a little subscript here with a capital F, and that just indicates, hey, maybe it's not actually the integer 0. So for example, you guys have all had linear algebra. Suppose you had a set of a bunch of, vectors. Okay? If you have a set of a bunch of vectors, the 0 vector would literally be the vector of all zeros, however large your vector is, or whatever dimension your vector's in. Technically speaking, that's not the integer 0, but it sure still acts like a 0. Okay? Now, the technical term here is what's known as the additive identity. You don't need to remember that, but this guy would be called additive identity, or layman's terms, the 0 element. Okay. And the fourth and the last thing that you need in order to be an abelian group, and with respect to addition is just saying the operation that we're looking at throughout all four properties is addition, is you have to have, in layman's terms, a negative. Okay? So pick any element you want in your set. We'll call it A because we're lazy. Then there has to exist another element in your set. Maybe it's the same element, maybe it properly is a different element. We're going to call this guy negative A. Please note at this point in time that's not negative 1 times A. This is a brand new symbol with negative A altogether. So there's got to be some other element in your set where if you add that guy that we're going to call negative to its original element, you better get that 0 element that you already have to have. Okay? Now, technical terms for this negative element is what's known as the additive inverse. Again, I don't care if you remember that name or not, but in terms of properties, it's the thing that when you add it to the original element you started with, you get back a 0. Okay? And that's it. That's an abelian group with respect to addition. Again, you don't have to remember this title right here, but those are the four properties you need. Associative, commutative, 0 element, negative element associated to your set. Now, that's half of what you need. Notice we've only talked about addition. The set also deals with multiplication. And it turns out the second thing we have to have is we have to have that this set is an abelian group with respect to multiplication. Don't overthink it. We're going to do the exact same thing but now with multiplication. So first thing is you have to have the associative property with respect to the multiplication operation. So here, multiplication again is a binary operation. So you multiply any two guys together, then multiply the third element together, and it's got to be the same no matter which first two elements you chose. So here, again, all those elements, any old elements in your original set. Second property is you have to be commutative. So this means it doesn't matter what order you multiply things together. Third property is you had to have, well, previously we did zeros and inverses, but that's not going to work with multiplication. So what happens here with multiplication is you have your identity element, and this one properly is always called an identity element. Technically, it's the multiplicative identity, but most people just abbreviate or shorten it to identity. And this one here is, again, some element in your set, where if you multiply that element in your set by any other element, you should get that other element A. Notice this is the exact same characteristic we had up here in 1C, except we did what? We replaced the multiplication and addition, and we replaced the 0 now with the symbol for 1. Okay? Just like we described before with the 0 element, this guy here could actually properly be the integer number 1, but it could also be something that acts like the number 1 in your set. So for example, maybe your set F is comprised of all 2 by 2 matrices. the identity element in the set of all 2 by 2 matrices is literally that 2 by 2 identity matrix. So you've got ones on the diagonal and zeros everywhere else. Okay, so again, we have this subscript here just to indicate maybe you're not really just the integer 1, maybe you're whoever's acting as the identity in your set. Last property to get an abelian group with respect to multiplication is take any element in your set, make sure you don't pick the 0 element, then it turns out there's an inverse, technically a multiplicative inverse. However, most people shorten that just to inverse. Okay. Notice right now, this guy is also properly a new symbol. It does not necessarily mean 1 over a right now, although in many, many fields that's really what it also means, but it is in fact its own proper little symbol. Now, how do we define this guy? We define that you multiply your inverse times the original element a, and you better get back your identity element, your 1, if you will. Okay. Notice the 0 element is not defined to have an inverse. That also follows. Think if your 0 element really was the integer 0, if you tried to take the inverse of 0 or 1 over 0, as happens in real numbers, it's undefined. Okay. So, key bits. Your set, in order to be a field, must be an abelian group with respect to addition. So that means these 4 properties. And it also has to be an abelian group with respect to multiplication. So those additional 4 properties. Notice the 4 properties in condition 1 and condition 2 are exactly the same. You just switched out whether it's addition and multiplication. It's one of the reasons I like this way of categorizing the definition of a field. One last thing, and the last thing is the how you combine both addition and multiplication. And this guy here is the distributive law. Technically speaking, there's 2 of them, but since we already know that both addition and multiplication are commutative, you don't actually have to write them both down. So this says if you add any 2 numbers together and then you multiply by a third, you can totally distribute through and have done the multiplication first and then add. And that's supposed to work for any 3 elements in your set. Okay. If all 9 of those properties hold true, then, and you're closed under addition and multiplication. So you could sort of think about this as 10 properties. If all of those conditions hold true in your set, that's when you have a field. Okay. Now, how are we going to use it? We're going to use this less in verification of fields and more in the sense of, hey, blank set is a field. Now we automatically get all of these properties. So let's look at some examples. So here are 4 examples, and we're going to look to see whether we think they're going to be fields or not fields. What I would recommend you doing right now, pause the video, go back to grabbing that definition of a field, and just as a heads up, there is a handout in this section that lists out all of those properties associated with a field, so this might be the time to go and grab that and have it in front of you. Okay. So pause the video, check to see what you think in terms of these 4 sets, if they're fields or not, and these are our 4 very common sets of numbers. Okay. So I'm giving you a few seconds to do that because I'm assuming you're going to pause the video and then we'll talk about these. Alright, so I'm assuming at this point you've already looked at least a little bit over these 4 different sets of numbers and have a guess on who is a field and who is not a field. So if we look at real numbers and you go back to definition of a field, think about all of this stuff in terms of real numbers. If you add any 2 real numbers, is it a real number? Yep. If you multiply any 2 real numbers, is it still a real number? Yep. So we're good on the first condition. Now, we jump down into the actual properties that we're going to check out. And under addition, if you add 3 real numbers together, does it matter how you group them? Nope. If you add 2 real numbers together, does it matter the order in which you add them? Nope. Is there a 0 element in your set of real numbers? Yeah, the number 0. Now, if you take any real number, can you always find a negative? Yep, just multiply it by -1. Okay. Now let's look at multiplication. If you take any 3 numbers that are real numbers, does it matter how you group these multiplications here? Nope, you'll still get the same number either way. What about order? Does it matter the order in which you multiply them together? Nope, you'll still get the same real number. is there an identity element in the real numbers? Yep, the actual number 1. And are there inverses for all your non-zero numbers? Yep, just say 1 over whatever the number was. In other words, take the reciprocal. And lastly, if you add two real numbers together and then multiply by a third real number, can you actually distribute through? And the answer is yes. It turns out fields were actually very much developed to mimic what happens with real numbers. So it turns out with our real numbers, this guy is definitely a field. Okay. Now, let's jump back and check out our set of rationals. And remember, our set of rationals is what? It's all numbers that can be written as a fraction. So it includes all of your integers and then all of your guys that can be written as fractions. It does not include things like square root of 2 and e. Okay. So if we go back to our definition of our field, oh, that was too far back. Okay. So think now fractions. If you add any two fractions together, will you still get a fraction? Yep. Might be an integer, but an integer can always be written as a fraction, so we're still good. If you multiply two fractions together, will it still be a fraction? Yep. And I'm going to jump up to the technical term now of rationals. If you take any rationals and add them together, does it matter how you group them or the order in which you add them together, so those two together? And the answer is nope. You're still going to get some rational number, so some fraction or integer. And I'll go ahead and jump down here to multiplication as well. I have a tendency to do these four properties sort of all at once. So if you multiply your fractions together, does order matter? Does it matter how you group them? Nope, you'll still get the same answer. It's totally fine. So now let's jump back to addition. Do you have a 0 element? The answer is yes. It's going to be actually the integer 0. Now you'd write it as 0 over 1, but it's still just 0. Okay. Are you going to have a negative for every one of your numbers? Again, the answer is yes. Just multiply whatever your original fraction was or your rational number was by a negative 1. And you're good to go. So the only thing we have left to check are these last three properties. So, do we have an identity element that does this? And the answer is yes, it's just the number 1. Could we find inverses for all of our numbers? Non-zero numbers, caveat there, don't check 0. So any non-zero numbers, and yep, you just take the reciprocal of your fraction, no worries. And lastly, if you went ahead and tried to distribute fractions through, would it always work? And that you'd get the same answer on both of these two ways of writing it. And the answer is, yep, we're still good there. Okay. So that tells us that rationals are also a field. These two guys here will work with a lot in terms of some of the stuff that we're going to be doing. Actually, let me pause on that and we'll talk about that when we get to the next definition. So next thing we want to look at is the set of integers. So we'll go back over our definition. So you start off with integers, you add any two integers, still an integer, so we're good so far. You multiply any two integers, you're still an integer, so good so far. Add our integers together or group them in any way, still good. 0 element, yep, the integer 0. Negatives, yep, just multiply any integer by negative 1 and you've got the negative, so good there. Could we distribute? Add two integers, multiply, would it be the same as distributing through? The answer is yep, so we're good there. So go back here to abelian group with respect to multiplication. Now, integers, multiply them in any order or group them in any way, does it matter? Nope, we're still going to get the same answer either time. 2c, is there an identity element? Yep, it's the number 1. So the only one left here is 2d. And the question, of course, is pick any integer you want that's not 0. Will you always have the inverse? Okay. So let's go back here to the fields. First two were fields, integers. And the answer here is, check out that last one with an inverse. Turns out it's not going to be a field because to pick a really, really easy example, here it's 2 raised to just the number 2. The inverse of 2 would be 1/2 because 2 times 1/2 is 1. And notice 1/2 is not an integer, so that means your set of all your integers is not a field. In fact, it's too small to be an infinite field. Why? Because it's missing some of your inverses. In fact, all of them except for the inverses of 1 and negative 1 are missing. So, our first not field. So the second guy that we have here is our natural numbers. And if we go ahead and look at natural numbers, these guys are what? They're all integers, and you're not going to include your negative integers. So, notice we still have a number 2 that's a natural number. So do a quick check. is the inverse of 2, which is 1/2, is 1/2 a natural number? Hopefully, everybody is thinking no, so you could have used the same reasoning. And you also have a second reason, and that second reason here is pick on your same number 2. The negative of 2 is the integer -2, which is not a natural number because natural numbers don't include negative numbers. Okay? So this guy here is another set that would not be a field. I believe I have one more example. Excellent. So last example I've got here is in terms of symbols, capital M, which indicates matrix or matrices. Subscript tells you the size of the matrix. So here you've got 2 by 2 matrices. Now often what people will write after this in a little set of parentheses is what numbers are you plugging into those elements of your matrix. So you can think of it as either plugging in like integers, maybe you're plugging in real numbers. Let's go ahead and just assume we're plugging in real numbers. So if you look at your 2 by 2 matrices, and let me go ahead and jump back here to our definition of a field, and we'll walk through it. So if we're looking at 2 by 2 matrices, add any 2 by 2 matrix, you're still in your field. Multiply your 2 by 2 matrices together, you're still going to be a 2 by 2 matrix, so still in the potential field. Now, looking only at addition, order in which you add the matrices together does not matter, so we get the first two. Zero element, well, that's the 2 by 2 matrix of all zeros. The negative element, well, that's just multiply -1 by your matrix, so just flip the sign on all the elements, and that'll work just fine. In terms of distributing, you can totally distribute through, no worries right there. So we go back here to abelian group with respect to multiplication. Turns out here, I'm actually going to skip this first one for right now, and I'll go down to C. There is an identity element, it's the identity matrix, 2 by 2 identity matrix, so no worries there. And then if we go back here to 2b, this tells you that the order in which you multiply your 2 by 2 matrices shouldn't matter. You'll get the same answer regardless of whether you multiply one first or it second. Now, you guys have all dealt with matrices. Is it true that the order in which you multiply matrices together doesn't matter? Hopefully everybody said no. It actually does matter, the order in which you multiply your matrices. So this is something where if you have two matrices, A and B, if you multiply AB versus BA, you might get the same answer. It's possible, but more likely you're actually going to get two different products coming out. Okay? And that tells us we're not going to be able to be a field. Okay? So these are some of the common sets. The first two are fields, and both set of real numbers and the set of rationals are two that we're going to use tons and tons for the rest of the semester. And the last three are ones that we're not going to be able to use because we need fields. So we're going to start avoiding the set of integers and have to bump up to rationals. We're going to avoid natural numbers and matrices in this form. Okay. So let's look at, one last one. So last one down there is somebody called Q adjoin 2. And it turns out that Q adjoin 2 actually is a field. Okay. But first, let's talk about what this guy looks like. The Q adjoin 2 literally means you started off with all rationals and you threw in an extra square root. Okay? Now, you can't just include one extra element that is a square root because remember, you want to stay a field. So what you actually do is you say, all right, I'm going to add square root of 2 to anybody that it wants to be added to. I also need to multiply square root of 2 by anybody it wants to be added to. So this format here of a times b square root 2 actually allows you for all of the formats where you can add and multiply your square root 2 by anybody in the set of rationals or fractions. Okay. And it does turn out that if you go through all of those exact same steps that we just went through, this guy will actually turn out to be a field. Okay. All right. So if we go ahead and look at this next definition is something called the characteristic of a field. So the characteristic of a field is simply, it counts up how many times you have to add your one element together to get your zero element. Don't overthink this. This isn't completely crazy. Okay. Now, what happens if you can never add up enough ones together to get your zero element? Well, in that case, the characteristic of your field is actually 0. In other words, it says, all right, well, don't add any ones together. It's okay. You're just going to start with 0. Okay. The next thing is the actual definition of a Cartesian plane over some arbitrary field f. So your Cartesian plane in terms of symbols is a capital letter pi. Not going to lie, I couldn't get this to type up right. In handwriting, it actually looks like this, where it looks like a proper pi symbol. Capital Pi's just have all straight lines instead of the slight little curvy line on the top like lowercase pi's often have. Okay. Now this set F2 simply tells you the following. It tells you your points are defined by ordered pairs, where the first and the second coordinate are from your field. And it tells you that all of your straight lines are defined as ax plus by plus c equals whoever your 0 element is, where the coefficients a, b, and c are all from your field, and you can't have the coefficients on x and y both to be the 0 element. Notice that's the exact same definition that we've had in the past when we're dealing with basically all of our infinite models that we've had in the past. They actually were all Cartesian planes. Now, let us look at some common infinite fields, and these guys were the 3 infinite fields that we've had previously: real numbers, rational numbers, and then q adjoins square root 2. And let's look at the characteristic of these 3 guys. Okay. So for real numbers, I'm going to claim that the characteristic of real numbers is 0. Why? Because if you keep adding real number 1 together, what happens? It just gets bigger. So you get 1, then you add 2 ones, and you get 2, 3 ones, you get 3. It just gets a bigger and bigger and bigger integer. You're never actually going to turn around and equal the number 0. So you need to add exactly 0 ones together to get an answer of 0. Okay. In other words, 1 plus 1 plus 1 plus, and you keep doing it for however many times you think you need, this guy will never equal 0. So that's when your characteristic of the field equals 0. What do you guys think is going to happen with rationals? And it turns out the exact same thing. So here, the characteristic of rationals is also 0. Why? Same deal. You start adding a bunch of ones together. It's never going to equal 0. That's when you get characteristic 0 for your field. And it turns out the exact same thing is going to happen for this last guy too. Again, you keep adding a bunch of ones together and you're never going to get to 0. Turns out this characteristic of 0 right here is an indicator that you have an infinite field. Okay. All infinite fields, I shouldn't be this precise with that. In terms of what we're going to be looking at for us, if you have characteristic 0, that typically is going to tell you, hey, infinite field. It doesn't tell you which one, but it'll typically tell you infinite field. Okay. If you're interested in when the characteristic is not equal to 0, you need to stick around and look at the next video, because the next video is going to talk about when is this characteristic not going to be 0.